Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In my previous lecture, we have discussed about the UNet architecture and its use in image segmentation. In today's lecture, we will discuss about UNet with attention and few evaluation metrics for image segmentation. So we will start with what is UNet with attention. Attention UNet is an attention gate model for medical imaging that automatically learns to focus on target structures of varying shapes and sizes. Models trained with attention gate implicitly learns to suppress irrelevant regions in an input image while highlighting salient features useful for a specific task. So as we know, segmentation itself takes out the important region from an image, and UNet with attention is made so that in such a way that it suppresses irrelevant regions in an input image and highlights the salient features which are useful. So it was first introduced with the paper in 2018, Attention UNet Learning Where to Look for the Pancreas by Ozan, Okate and et al. Okay, and I have taken one picture from this original paper itself, where we will see this is the ground truth of a pancreas. Okay, so this is a medical image and this is the pancreas region, which is the ground truth, which is marked with highlighted with blue color. Okay, now this B, the image B, it is showing the pancreas, highlighting the pancreas. So this is the ground truth one. Whatever is shown here in blue, that has been highlighted here. Now this, the number C, the image number C in this the set, it shows the segmentation that is done using UNet architecture. And if we see, these red arrows shows that there are two places where it is not matching with the ground truth segmentation mask. Where it is, one is this portion where the shape looks like a little going inside, which is not the case in the ground truth, whereas also in this place this shape is a little different from the ground truth mask. And this, the D figure, actually it is the output of UNet with attention. So here we see the preciseness with which the segmentation have been done when using UNet with attention is much better than only with UNet. Okay, so this gives an idea what exactly is the idea of UNet with attention. We use some attention mechanism to focus and get more precise and accurate segmentation of the portions of our interest. Okay. Now we will see what is attention UNet segmentation model. How does this model look like, or how it works? What is the architecture? Suppose I have an input image of size height h1, width w1, and the input channels are d1, and this is the number of output channels, and this blue means there is a convolution, 3 cross 3 cross 3 convolution with ReLU, and it is 2 times the convolution is happening. So there is 2 layers of convolution, after which we get, there is no change in the spatial dimensions h1, w1 and d1, and f1 is the output number of channels. So after this 2 layers of 3 cross 3 convolution, there is a max pooling layer which reduces the spatial dimensions h2, w2 and d2. As we can see, there is a reduction. Max pooling 2 cross 2 means it will get halved, the spatial dimensions will get halved, and here there is d2. d2 comes actually because of the convolution operations which is shown here. So there is no change in the channel number due to max pooling, but the channel number have changed due to this convolution operations. Then we have another 2 layers of convolution with the same spatial dimensions, and then again a max pooling layer where the dimensions get reduced, and again 2 layers of convolution, 3 cross 3 cross 3 convolution, and with the same spatial dimensions and maintained, because 3 cross 3 convolution doesn't change the spatial dimensions. Spatial dimensions get changed when there is a max pooling, which is this part. So H3W3D3 becomes H4W4D4. So these are the changes that are there. And once again there is convolution, 2 layers of convolution, and again that is the feature map that is coming, and we can see all the dimensions have changed, basically they are halved. And then comes the up convolutions or upsampling, where again it goes back to the previous feature sizes, similar like UNet architecture. Now here the difference is coming here. So we know there is a skip connection that comes from the encoder part of a UNet architecture. Similarly here also it is coming. So this is a skip connection coming from the encoder part, and there is a concatenation of this block with the part that is coming from the decoder, but the difference is there is an attention gate here. So this attention gate, what is its function? It doesn't take all the information that is present in the encoder's layer. So it creates some attention score, and pixel wise it gives some attention value to that feature map which is coming out from the encoder, and whatever is having high attention will go and sit there. That means we are suppressing some irrelevant information that is not required for my application, and only allowing a portion of the encoder's features to be going and sitting there. So that is the difference here. So attention gate is here, and if we see, the attention gate gets 2 inputs. One is from the encoder, that the blue that the green dashed line, and another one comes from the decoder, which is called as the gating signal. Okay, so the attention gate gets 2 inputs. One is from the encoder layer, another one is from the gating signal, another one is from the decoder, the deep regions of the decoder, and it is called as the gating signal. And then once again there is 2 layers of convolution, and which is followed by another layer of upsampling. And similarly in here, after this upsampling also, we know in upsampling the spatial resolution or the spatial dimensions becomes doubled. So you can see the dimensions have changed here also, and this is the skip connection that is coming from the encoder layer to the decoder, and this is the concatenation with the attention gate here. This attention gate once again is getting one signal from the decoder part also, and one coming from the encoder, and the same thing continues. This means there is 2 layers of convolution, 3 cross 3 convolutions, and then we go back, there is another upsampling which takes it to the original input size H1 W1 D1, and with F1 output features, and there is concatenation here that is coming from the skip connections. The concatenation is happening because of the portion that is coming from the encoder layer with the attention gate in between, and here also there is a gating signal which is coming from the decoder. Then there is another layer, another 2 convolutions plus ReLU, and this is basically this is the segmentation map, which is having the number of output features is NC, that is the number of classes that are there in the segmentation map, and then H1 W1 D1. Now there are 3 channels here, H1 W1 D1, because usually the medical images are 3-dimensional CT scans images and MRI. They have a depth information also. That is the reason H1 W1 H1 is the height, width, and the depth also is there in all these blocks. Okay, now So we have understood that the encoder and decoder structure is similar to normal UNet. Only thing that is different here is when the skip connections are happening between the encoder and decoder, there is an attention gate which takes one input from the encoder, one input from the decoder, and then it does some operations which we will see what operations it is doing, and then only a portion of the feature map is getting added, concatenated here. Okay. So this is the attention UNet segmentation model, and then we will look into attention gate mechanism. What exactly is happening inside that attention gate, the round colored structure. So the core idea, as I was telling, is instead of directly concatenating encoder features to the decoder features, we first weight the encoder features with an attention coefficient, the number between 0 to 1 for each spatial location. So the entire image is broken into pixels, and each and every pixel will get an attention score. Now that attention score, when multiplied with that pixel value, whichever is having higher value will go towards the concatenation with the decoder blocks layer. So if we see, there is a gating signal that comes, and there is a the gating signal, we call it as G, which comes from the decoder. And what does this gating signal have? It contains the textual informations but in coarser scale. Why? Because we know when the image comes through the downsampling in the encoder region and then reaches the bottleneck. The bottleneck place is the region where you have most compressed features, very important features, but in the most compressed form. When it is compressed, when any image is compressed, what happens is the resolution goes down, and when the resolution goes down, there is no finer details. Now, but it has the information, okay, but in a coarser scale. It doesn't have the fine details. Yes, it may see the pancreas or the tumor, it can locate, that information is there, but the details of the pancreas or the tumor in any biomedical image may not be, it will not be present there. It is because it is low resolution feature map. Low resolution deep feature maps are coming from the decoder. So the gating signal, as it comes from the decoder, it has low resolution deeper feature map. Okay. And coming to the encoder feature map layer, so what exactly is coming from the encoder? So it is XL, X to superscript is L. So the encoder feature map of layer L. Okay. So this is the input that is coming from encoder. Now this feature map from the encoder is coming through the skip connection we have seen, and it is a high resolution image or feature map because it is a part in the encoder where we have not gone to the minimal compression, not minimal, to the maximum compression. Okay. So the resolution is much better in this encoder feature map. And then what we see is this gating signal goes through 1x1 convolution, and this is a it's a filter, and here also it goes through a 1x1 convolution. Both WG and WX, these are learnable kernels. That means what are kernels basically? These are they have some numbers. These are matrices and which are having some numbers inside, and these numbers are nothing but the weights. Now these weights keep on getting trained during the keep on getting changed during the training process, and that's the reason we call them as learnable kernels. Okay. So both gating signal and the encoder feature map both are going through 1x1 convolution with learnable kernels. Okay. Now this is a figure that I have taken from the original paper. Now we have the input image, and then this is the downsampling, then these are the attention gates, and we will see here and then there is the up convolution or up sampling, and finally we get the segmentation map as I was discussing. Now suppose you take this attention gate. Now, this is basically, what is it? It is your gating signal, the green one, okay? And this is your skip connection, and it is taking the encoder feature map, okay? Now, let us consider it is a 64 cross 64 cross 64, the size is for the gating signal, and encoder feature map is 128 cross 128 cross 128, okay? Now, why there is a difference? See, if the gating signal is coming from here, your encoder feature map is coming one layer up, and we know if the feature size here is 64, height, width and depth 64, 64, then this will be double of 64 because it's above this layer, okay? So, H3 should be greater than H4. So, the encoder feature map is 128 cross 128 cross 128, okay? Now, we will see what happens. So, this is once again I have taken the attention gate operations, this picture from the original picture or original paper, and we are here right now. So, we have the gating signal, we have the encoder feature map going through 1 cross 1 convolution, and what exactly is happening? Feature map, these are going through 1 cross 1 convolutions. Why we need this 1 cross 1 convolution? Because we want to bring both these into the same dimensions. So, if here the stride is 1 and here the stride is 2, if the stride 1 cross 1 convolution with stride 2 is done, then this feature size becomes half, which is 64. So, and if we have number of filters 128 here, both the places, then the output feature map size is 64, 64, 64 cross 64 into 128. Here also it is the same. Now, why do we want both these things to be in the same dimensions? Because that is something we want to do here is a element wise addition, okay? So, the element wise addition is done for between the gating signal and the encoder feature map, okay? And whatever output we are getting, that is going through your this part, which is your ReLU. ReLU, we all know it changes the negative values to 0 and linearly increases with the whatever positive values are there, it shows that one. So, the ReLU activation function, it's a nonlinear activation function that, so your whatever weights you have got, they are passing through the ReLU, okay? And then we come to this block, which is again 1 cross 1 convolution, number of filters is 1, and here what happens is it brings down the channel numbers to 1. So, we have only 64 cross 64 cross 1, okay, here. Now, then we go to this sigmoid activation layer. What does sigmoid activation layer do? So, whatever output is coming from here goes to the sigmoid activation layer, and this, what is the function of sigmoid activation layer? The sigmoid activation function, it changes any values or squashes any values between 0 and 1. So, what was happening here, ReLU was giving any value between 0 to infinity, which is possible for ReLU activation function. Whichever positive value is there, it may range, but I want some value between 0 and 1. Why do I want between 0 and 1? Because at the end of this entire process, I want some attention score to be calculated, and the range of that attention score is between 0 and 1, okay? 0 means minimum attention, 1 means maximum attention. So, the sigmoid activation function is kept here, which brings all the weights between 0 and 1, okay? And then what is the next one? There is a resampler here. What is the function of this resampler? See, through all these processes, I have changed the dimensions of the encoder feature map. Now, if I want my attention score to be multiplied with each and element wise multiplication of the attention score with the encoder feature maps each pixel, then I should have the same size, okay? The sizes, if the dimensions are different, I cannot do a element wise multiplication. So, the resampler upsamples to the original size, which is the encoder feature maps size, And then what happens is we are here in this last block. What we are doing here, we are taking the encoder feature map and the resampled, whatever is coming from all these attention gates, all operations, and we are doing a element wise multiplication. You can understand this one like each pixel is getting multiplied by some value alpha. Okay. Now what is this alpha? Alpha is your attention score. Now when you are each pixel value is getting multiplied with alpha, then some pixels are getting higher attention with high alpha value. When alpha value is small, that means those pixels are getting lower attention. Now whichever is getting higher attention, those only will go and concatenate with the decoder's layer. Okay. So this is the full working of the attention gate. Okay. This is how what we do is in attention or UNet with attention, we try to give more attention to the specific regions of interest in the image, and we try to suppress the irrelevant background, the noises and other things that are not required for a particular application. Okay. And this attention gate helps us to create some attention score, which we multiply with the encoder's feature map, then concatenate with the decoder's feature map, and then finally get the segmentation map. Okay. So that's about the attention gate mechanism. Now we will go into the evaluation metrics for image segmentation. So till now we have done what is image segmentation, what are the architectures that are used in image segmentation, the UNet with attention, both we have seen, and now we will try to look into what are the evaluation metrics for image segmentation. Okay. So one of them is intersection over union. So what exactly is this intersection over union? It is also known as Jaccard index. So intersection over union is modulus of P intersection G by modulus of P union G. What is P and G here? P is my predicted mask, G is the ground truth mask. P intersection G is pixels correctly predicted as the object, okay, which is the true positives, and P union G is all pixels predicted or actually belonging to the object. Okay. So we will see with an image here. So this is my P, which is my predicted mask, and this is my ground truth mask. And the intersection point P intersection G, this gives actually the true positives, means the prediction is matching with the ground truth mask. Okay, divided by the union of P and G. So everything that is between the predicted also is fully there, the ground also is fully there together, and there the overlap part is there. Okay. So this is P union G. Okay. Now this value ranges between 0 to 1. If the value is better, if the value is higher, it is better. That means your P intersection G value is high. That means the overlap portion between your predicted and the ground truth mask, that is more. Okay. So that is about intersection over union evaluation metric for image segmentation. Okay. Now these are few terms which we will be using more often in my next 1 or 2 slides. True positive and false positive and object detection. We will just have a look into what are exactly they are. So suppose I have this image, it's an AI generated image of a lady walking in the street, and my object of interest is this human figure. Okay. Now if I have a bounding box around the figure, then this is my true positive. Okay. So the model is telling, okay, this is your region of interest, which is the human figure. If my bounding box is somewhere here, which is not the human figure, something else, that is false positive. The model is telling that this is the human figure, but actually the human figure is somewhere here, then it is falling under the category of false positive. Okay. Then what are true negative and false negative in object detection? Once again the same image I have taken, and if you see, this is my background. Okay. And this is true negative, means my interest region is the human figure and the background is my negative or of a region which is not of my interest. So, this is the true negative, it is telling the background as a background. Whereas, if it tells this portion as the background, that means it is false negative. So, for me the positive part is the human figure, the negative part is the background. So, when it is telling the human figure, it is predicting as the background, then it is false negative. Okay. Now, can we represent intersection over union in terms of true positive, true negative, false positive and false negative? Let us have a look. Okay. So, we know IOU equal to intersection between P and G divided by the union between P and G. Okay. So, this is union and this is the intersection. So, we know, and it can be written as true positive divided by true positive plus false negative. How it is happening? So, true positive means your prediction is actually correctly predicting, or your prediction mask is actually matching with the ground truth mask, okay, which is nothing but your this portion, intersection part. Okay, your prediction and your ground truth are overlapping. Now, in this union part, we have this overlapping part which is your true positive. Now, let us look into this region. So, this region is basically your model is predicting it as the mask, but actual mask is not that one. So, this is your false positive. Whereas, this portion if we see, this is your ground truth, but your prediction is telling no, this is not the mask. So, this is false negative. Okay. So, the IOU or intersection over union can be written as true positive divided by true positive plus false negative. Okay. Now, for semantic segmentation, that means if there are various class like one pixel value for dog class, 1 pixel value for cat class, 1 pixel value for the road, 1 pixel value for the sky. So, if there is a semantic segmentation prediction, the IOU score is calculated for each class separately and then averaged over all the classes to provide a global mean IOU score. Okay. So, that is for semantic segmentation prediction. Then we go into dice similarity coefficient. Now, what is exactly this one? Dice score or dice similarity coefficient is equal to 2 into intersection between P and G modulus plus divided by P plus G. That means modulus of P plus modulus of G, which can be shown pictorially like this. So, this is the intersection point and this is the intersection point and twice of that one divided by there should be one 2 here, I will write it pen. So, this should be 2 into this one divided by P plus G. Now, so we as all we know, P is the predicted mask, G is the ground truth. Okay, and this can be written as 2 true positive divided by 2 true positive plus false negative. How we are getting this one? It's very simple. 2 is here and this is nothing but our true positive. We have seen it in our previous slides only, and here it is divided by. Now, when we are taking these two separately, what is happening? This portion comes 2 times, right? One for this P mask, one for the G mask. So, 2 TP comes like that, and whatever is remaining other than this overlap part, that is one is my false positive, which is this part of P outside this overlap, and then false negative, which is this part of the the ground truth mask outside the overlap region. Okay. So, this is about dice similarity coefficient. Then we have some, dice similarity coefficient is often used in medical image segmentation for very small or thin structures. So, these segmentation task itself is heavily used in medical images, and this dice similarity coefficient is used when the structure is small or very thin. Okay. Then we have another evaluation metric, pixel accuracy. It is nothing but correctly predicted pixels by the total number of pixels, and that can be written as true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. So, correctly predicted pixels, it can be of two types. No? It can be the true positives, that means it is telling my human figure as the human figure predicting, and also true negative, it is telling the background as the background. Okay. And here whatever is there are true positive, true negative, false positive, false negative, total number of whatever is there, that gives me the pixel accuracy. Total number of pixels are there in this one. The correctly predicted pixels divided by the total number of pixels give me the pixel accuracy. Then we have precision and recall. Precision tells you out of all the pixels which the model marked as positive, how many were actually positive. Okay. So, precision tells me the true positive divided by true positive plus false positive. The model may give some false positive also. So, true positive first plus false positive is in the denominator, and these are all the positive marked by the model. All the cases that are marked positive by the model, out of which only the true positive ones are the correctly marked one. So, precision gives us that value. And recall tells you out of all the actual positive pixels, how many the model successfully found. Okay. So, recall equal to true positive divided by true positive plus false negative. So, out of all the actual positive pixel values, so which is your true positive, how many the model successfully found. Okay. So, how many the model successfully found means it is summation between the two positive plus the false negative. That means false negative means that also those pixels also it is telling as human figure. Okay. If my positive is a human figure and the negative is my background. Okay. For example, let us take if a model says 100 pixels are of class 1, 80 of them are correct which are true positive, 20 are wrong which are false positive, then precision becomes 80 divided by 80 plus 20 which is 80 divided by 100, that is 0.8. Okay. If the model missed 40 actual class 1 pixels, this is false negative. In that case, recall equal to 80 divided by 80 plus 40 which is 0.67. So, this is about precision and recall. Okay. So, with this one I come to the end of today's session. So, before I conclude, let me summarize what we have learned today. So, we have looked into UNet, attention based UNet or UNet with attention, where the structure is very similar to normal UNet architecture. It has an downsampling path and the upsampling path, encoder and the decoder with a bottleneck. Those things are same. Only thing is whatever is coming from the encoder and getting concatenated with the decoder during upsampling. So, there is an attention gate which decides which part of the encoder's feature maps are relevant and which are irrelevant. It only takes those relevant pixels from the encoder feature map and then adds into the decoder feature map to give more finer details to the region of interest. Okay. So, that is the main idea of your UNet with attention or attention UNet, and then we have discussed about the mechanism how the attention gate is working. Attention gate has two inputs. One is coming from the decoder which is called as the gating signal, and then we have one signal coming from the skip connection from the encoder layer. So, these two are coming into the attention gate, and inside the attention gate we have seen what are the operations that are happening. There is their 1x1 convolution, then which brings both of the decoder and the encoder's feature maps into the same dimensions, and then there is element wise addition, and then that output goes through the ReLU activation, and then from the ReLU activation it goes through another layer of 1x1 convolution, and then it goes through sigmoid activation. So entirely in this process, basically we are trying to learn the filters that we are using, the 1x1 convolution filters. These are learnable kernels, and when the output from the 1x1 convolution comes into the sigmoid, the weights are actually changed between 0 and 1. And then from the sigmoid activation function, then there is a resampler which resamples or takes it to the original input images size, because we want to do pixel element wise pixel multiplication with the attention score that we are getting out of the softmax, and for that one this resampling is required, which takes the image to the previous original size. And then there is a element wise pixel multiplication of the encoder's feature map with the attention scores, and finally we get the portions which needs to be concatenated. Okay, so that is the overall working of the attention gate. Then we have looked into the evaluation matrix, the intersection over union. Then we have seen the dice coefficient, and then pixel accuracy. Then we have seen the precision and recall also. So with this one, I conclude our session on image segmentation, and in my next session we will be talking about object detection and algorithms for object detection. I hope you got an understanding about how the attention unit works, how attention mechanism is incorporated in the unit architecture, and how it is helpful. So let me conclude the session with this one, and in the next session I will meet you all with the object detection task and algorithms. Till that time, happy learning. Thank you.